Okay, so the first activity we're going to do here is the sheet metal working lab. And the sheet metal working lab ends with this product, which is our sheet metal tray. I've got a drawing here of our layout with a couple of notes on it, and I'll just go over a couple parts of the sheet metal tray before we get started. So this layout is going to be the 2D shape that we start with before we start bending. So there's a few notes on here that there's some relief holes that are punched in the corners. That's to keep metal from squeezing out and making a sharp corner. So here's the corners of the box. To make sure that this doesn't have a sharp burr on it, we're going to remove a little bit of material from there. Similarly, we've got some tabs here. These tabs are located on parallel base lines. You can see that these lines we're going to bend up the sides to make the base, and these tabs are going to give us a place to locate a weld so that we can fasten the box together. And then the last note you'll see here is a hem. We're going to leave a little bit of extra material on the edges to produce this safe edge up here, known as a hem. It's just like what you have on your clothing. Now this is a display piece. It's a little bit shinier than the work pieces we're going to be using, and that's probably the next place to carry this discussion. So the work piece that we're going to be using is going to be cold rolled steel. So when we look at a piece of cold rolled steel, we see that it has excellent surface finish. It's very flat, it's dimensionally very stable. When we talk about hot and cold rolled steel, the two common types of steel that we see used for mild steel for fabrication, hot and cold rolled steel have fairly distinct differences. The cold rolled steel, because it passes through the rollers after the hot rolling process, has a much better finish, can go on to paint without a lot of additional processing. The hot roll finish has this bluish oxide layer that you get from it being cooled directly from being orange hot coming out of the rolling mill. To take a little bit closer look at the differences between these two types of material, I have some structural pieces of steel here. They're a little bit thicker. Again, we have cold rolled on the left and hot rolled on the right. The cold roll also has better finish, although it may not be quite as nice as the very thin sheet. But this piece of bar stock, which is 3/8 thick, still has a very flat surface. If we turn it on its edge and we look here at the side, we'll notice that there's a very square, sharp corner here. This edge is very sharp, and we can rely on the side to be very square. That's the result of the additional rolling process, which imparts not just better dimensional stability, but also some better surface finish. When we look at this piece of hot rolled, the hot rolled surface is actually rounded here on the edge. The surface finish is a lot coarser. This is a much less expensive piece of steel. Still serves a lot of really good purposes, but in terms of finishing, this is going to require some extra work. So when we want to produce our sheet metal product, we're going to start over here with a piece of cold rolled steel. So the next step is to get a piece of stock. It's large enough for us to put our layout on. Scribe out marks all the way around, shear out the blank, and then we'll go through a variety of forming processes to actually get that bent up into the box. Then the last step will be to add these welds here to hold the box together. Okay, so now I've selected a piece of stock that will be large enough for me to get my workpiece out of. I've cleaned it to take any oil off that could interfere with the layout process. And I'm going to transfer some measurements from my layout here onto this using a variety of scribing tools. Now normally when this course meets in person, I would assign each group different dimensions so that each box would be different. For the purpose of this video, I'm going to assign myself some arbitrary dimensions of a 4x4 inch base, a 1 inch high wall, and we'll say that this is going to be a 1/4 of an inch hem. So all these dimensions will be scribed and laid out on this workpiece so that I can then trim this out and start forming up the box. One of the things that I don't want to rely on though is that the workpiece is perfectly square all around. If I were to measure from each edge and there were to be some problem with the squareness or rectangularity of the workpiece, then that would pass on to my finished product. So what I'm going to do here is I'm going to use a machinist square, and I'm going to check each of these corners for squareness. I'm going to find a corner that I can trust is very square, and that will be my reference corner right there. So here is my reference corner, and then I'll mark it here as well. So now that I have a reference corner, I can scribe my marks perpendicular to each other all the way across, and then my workpiece will be nice and square as I go. The lines that I'm going to scribe are going to be the outer dimensions, the outer parameter boundaries of the box, the hem lines, and the base lines. And then using the intersections of the base lines and hem lines, I'll be able to scribe out the remainder by hand. In order to transfer the layout that we have on our drawing here onto our steel sheet, we're going to use a process called semi-precision layout. And there's a few tools that we're going to use to make those marks accurately and clearly. So the first tool is this. This is a precision surface plate. It's a piece of granite, and it's very flat across its entire surface. It deviates from perfect flatness really no more than a few millionths of an inch. This gives us a good reference surface to use our tools, so we have a nice flat plane from which to make our measurements. The scribing and marking is going to be done using this tool. This is a height gauge, has a dial here and a digit readout, has a carbide tipped stylus, and we're going to use this to set for our different heights and scribe our marks onto our steel. In order to make sure that the workpiece is square to this reference plane made by the surface plate, I'm going to use an angle plate to hold the workpiece square. A few moments ago you saw me spraying the workpiece with layout fluid. Layout fluid is a blue dye, and we put that on the steel because the marks we're going to be making are very, very fine. They're so fine, in fact, that it may be difficult to see them. But we want that very fine line because that's how we get the precision of this process. So in order to use our height gauge correctly, we want to make sure that it is zeroed out. So we're going to lower the stylus here very gently onto the workpiece, onto the surface plate, make sure that it reads 0. Zero out our digit counter. I have my workpiece here, and I've made a little scratch mark up here to show where our reference corner is, and I have the same reference corner that we marked here on our workpiece drawing. And so I'm going to scribe lines emanating from that corner, referring to all of the necessary lines we'll need to cut out this shape. So to start, we're going to scribe lines for our 1/4 inch hems, then we'll scribe lines for the bottom of the sides, and so on until we have the entire flat layout made. The dial here on the height gauge is in tenths of an inch. One revolution of this dial is 1/10 of an inch. So to get to a 1/4 of an inch, which is the first scribe mark for our hem, I'll go to 2.5 revolutions. And then I will position the workpiece here against my angled plate. And then by applying some very light pressure, I will run the scribe across the workpiece. So here you can see that the layout die really does help to clarify where we've made our marks. So the next line that we're going to make is the bottom of the sides. So when we look at our drawing, that's going to be a line right here, giving us the outline of the base of our tray. Since we have 1-inch high walls and 1/4-inch hems, that line has to be marked at 1 1/4 inches. And we'll go through and we'll scribe our marks. And I'll continue on. Since we have a 4-inch by 4-inch base, the next boundary is at 5 1/4 inches. After we make that boundary mark, we have to scribe the lines that will represent the top of the opposing sides. That's 6 1/4 inches. And then lastly, we want to scribe the very outer boundary of the box. That means we have to add up all of the dimensions for the base, 2 sides, and 2 hems. In this case, that's going to be 6 1/2 inches. And there is our completed layout. Once the lines are scribed on the height gauge and surface plate, we have a few more marks to make to give us the lines that we need to complete this shape. When we look at our drawing, you'll see that there are tabs here sketched out. There are also bevels cut off of the hems to help give it a nice clean edge. And we need to transfer these lines now onto our flat layout. The lines that constitute each tab are the product of a line made between an intersection of a hem line and a base line, and then the other intersection of a base line and a hem line. In order to produce that here on our steel sheet, I'm going to use a ruler and a hand scribe, and I'm going to locate here the intersection of a hem line and a base line, and then another hem line and a base line at the same corner. And then I'll lay my ruler across there, and I'll generate this line which constitutes a portion of the tabs. I'll go around to each corner and do that. Now to generate the other line that constitutes the other side of the tabs, I'm going to lay my ruler across the intersection of each baseline and baseline at opposing corners. It's going to generate a line 45 degrees across the center of our drawing. And there you have it. That is the product of our semi-precision layout process. Now we can go on to some of our shearing processes to start cutting this into the shape that will form up into our tray. Once we've laid out the sections of our flat layout that you saw on the surface plate, the next step is to shear them using this machine, which is a squaring shear. The squaring shear is foot powered, like so, and it's named a squaring shear because it has guides on the right and on the left that you can align your workpiece with so that it makes straight cuts. There's a clamp bar to keep the workpiece from moving, and then this top knife is actually on an angle. The reason for that is so that it doesn't have to cut all the stock at once. It can cut across like a pair of scissors. There's a back gauge here that you can use to make cuts of repeated length. But for what we're going to do today, we're actually just going to cut the outside boundary first. Those are the two edges that were not the reference edges that we used. So I'm going to cut this into the outer boundary first. And then those lines that we scribed using the intersection of the hem and base lines will be the next thing that we cut. So using this right side gauge, I'll line up the workpiece and shear off the excess material. Once we've sheared the blank square, I'll use the sight line down between this top knife and the clamp to line up and cut off the corners that we scribed. And there you have the trimmed blank. Now, I mentioned that here in the corners of the bases that we were going to want to punch out some small holes. And if you remember right in our drawing, you see them here as relief holes. Now, in order to do that, I need to mark the locations with a center punch. The reason for that is that I'm going to use this hand punch, which has a punch and die, which you'll see up here. And that punch and die needs something to locate on. So here, using the intersections of the baselines where I scribed my mark, I'm going to put a small dimple called a center punch that's going to help align the hand punch. Here you can see little indentations left behind. And then I'll use the hand punch to punch out our holes. Once the 4 holes have been punched to give us our reliefs in the corner, now I can cut out my tabs. Before I do, I just want to go back to our drawing and note that here and here, these tabs share one baseline. and then this baseline here contains these tabs. That's really important that we make sure we get those tabs on the same baseline, because if we don't, then they won't bend up together the way that we want them. In order to cut them out, I'm going to use a pair of sheet metal shears known as compound shears, named so because there are 2 pivot points. It gives us additional leverage to cut through metal with less effort. So here I'm going to cut out my first tab, and now that sets the baseline that I need to put my next tab on. Sorry, this baseline right here. So this tab now must be mirrored over here, and then here, and then here. So I'll go around, trim off these tabs. So now our flat blank is complete. It's a little bit not very flat right now, but we can fix that with a little bit of light tapping with a rawhide mallet. The next step in bending up our box, now that we've made our flat layout, is to put the hems on. Now, we scribed lines for the hems, but we don't need that to manufacture the hems. In fact, this machine right here, referred to as a bar folder, has a gauge on it that will allow us to set it for whatever height hem we want. So I can set it here for 1/4 of an inch. Now, if I want to, I can verify that my scribe marks are in the correct places as well. So by locating the workpiece, I can make half of a hem, so that's now bent over halfway. And then I bring the bar folder down to close the hem, and that makes our nice safe edge. We go around, complete the process. And then close all the hems. Our hems are finished. Once the hems are made, the next step is to bend up 2 sides of the box. We do that on a machine called a box and pan brake. Box and pan brake has movable shoes, a clamp bar, and then a front apron that bends up. We bend the sheet metal under these clamp shoes, and then we can bend it. And being able to move these clamp shoes gives us the ability to bend up the sides of boxes, which is how it earned its name, the box and pan brake. So I'm first going to bend up these edges here, the sides which have the tabs on them. So I'll clamp it, and then I'll bend up. Now, it's a little difficult to see in the video, but I actually have to bend past 90 degrees. I have to overbend, and that's because there's elasticity in the material. I'll go to the opposing sides next. And bend those up. So now that I have 2 sides of the box formed, it would seem logical that the next step would be to bend up these sides. I can't do that, however, because these tabs are now on the same plane as this side. They need to be tucked in a little bit more, and we use a hand working process to do that. In order to tuck in the tabs, I'm going to use a bench anvil and a tin worker's hammer to knock these tabs in. All I want to do is bring these tabs in just enough that they slide into the inside of these other edges. There we go. Now the tabs are just on the inside of the plane made by the sides of the box. Now we're ready to go back to the box and pan brake and fold these up. Here, back at the box and pan brake, I'm ready for the last step in bending up our box. To select some shoes that are appropriately spaced so that we can slide the box inside, and then position and bend the last remaining sides. That's our box. It's been formed. Now the last step will be to weld this together. The final step in assembling our box comes from the resistance spot welder. This spot welder has upper and lower electrodes, a little foot pedal, and when we push it down and we make contact with the electrodes, a timer will pass electrical current through the two pieces of the box. Because the electrical resistance between the copper and the workpiece is not as high as the resistance between the two workpieces, the two tabs of metal, that the two pieces of metal will heat up the most, melt, and create the weld. So I'll position the box here, and all I have to do is push down, and the weld is made. I'll go around and I'll complete welds on all four tabs. And the box is completed. We can see successful welds in all corners. Now that the box is completed, it's important for us to take a minute and just talk about one of the most important features of sheet metal working, and that's what's called bend radius allowances. You'll notice that when I added up all of the dimensions, I didn't account for any material that might be lost in the bend itself. It's very important to take that into consideration, otherwise the part will come out of size. And in fact, this box does not have all the dimensions that I started out with. I did that intentionally. It's supposed to be a learning opportunity for the groups. As they make this box, they follow all the instructions and do everything perfectly. When they're done, they find that they have a box that doesn't match the sizes I gave them. Now, it's a little different doing this online, but hopefully the same message gets across.